Separable equations can be solved by separating the variables and then integrating both sides. For example, let's solve dy dt equals e to the t over y squared. I'll multiply both sides by dt to get dy equals e to the t over y squared dt. Then I am going to multiply both sides by y squared to finish separating the variables. And now we'll simply integrate each side. On the left-hand side, I'll have 1/3 y cubed. And on the right-hand side, I'll have e to the t plus c. Don't put the plus c on both sides. They would just be combined anyway into one, so just put a plus c on the right-hand side. Now we do want to solve for y, so let's multiply both sides by 3. That'll give 3e to the t plus 3c. Now the thing is, if c can be any real number, and it can, it's an arbitrary constant, then 3c could be any number. So usually people just leave this as a c, because all we need is an arbitrary constant. It doesn't have to be the same arbitrary constant we had before. I think for this example in the notes, I'm going to go ahead and call it C1, just to help you understand, when you're looking back over your notes later, to help you understand why the C didn't get multiplied by a 3. It did, we just decided to give it the new name C1. And C1 can be anything, because C can be anything. Then last, let's take the cube root on both sides. And we get 3e to the t plus c1 inside a cube root. Now the c, or c1, whatever you want to call it, does have to be inside the cube root. You can't say, oh, well, if c1 is anything, then the cube root of c1 could be anything. I mean, that's true, you can say that. But the thing is, we can't split up our cube root. So I don't even have a cube root of c1 to be talking about. I can't say that's cube root of 3e to the t plus cube root of c1, because radicals just don't split up like that. So the c does truly have to be added to the 3e to the t first, and then the cube root taken. Let's try the next example. Let's solve dy dx equals x squared over y ln of y times 1 plus x cubed. I'll start by multiplying both sides by dx. And it looks like I need to multiply both sides by y ln of y. And you could certainly combine these two steps into one. That would be fine. I'm going to integrate both sides now. And the integrations are a little more complicated this time. Let's see, on the left-hand side, that does not look like a good candidate for substitution, so I'm going to use integration by parts. My u will be the ln of y, so du will be 1 over y dy. My dv will be y dy, so v will be 1/2 y squared. And then I have to go uv minus the integral of v du. So uv will be 1/2 y squared ln of y minus the integral of v du, which is 1/2 y squared times 1 over y dy. So at this point I have 1/2 y squared ln of y minus 1/2 times the integral of y dy. So what I'm getting there is 1/2 y squared ln of y minus 1/2 times 1/2, which is 1/4 y squared. I'm not going to put a plus c because we're saving that for the other side. On the other side, I will have a substitution I need to make. So for this side, let's let u be 1 plus x cubed. Then du will be 3x squared dx. So I will be putting in a 1/3 du for the x squared dx, which will give me integral of 1/3 times 1 over u du. So integrating that, I'll have 1/3 ln of the absolute value of u plus c. So what the left-hand side is equal to is 1/3 ln of the absolute value of u, but u was 1 plus x cubed, and then I have plus a c. This solution is implicit, meaning the y has not been solved for, and unfortunately, we simply cannot solve for y in this example. If we could, we would, but having a y squared ln of y and a minus y squared term, that's just not going to be possible. So we're stuck with this implicit solution.